Everybody, we are going to begin our second Flash Talk session. This session is focused on mission, instrument, and technology concepts that are currently in development. So these are the new ideas coming out of our researchers, many of which I've been looking at in the relatively near term. So I'm excited to hear more about what they're doing. And so we will begin with our first presentation by Angela Marusiak, LEMS-A3, sending seismometers back to the moon.
Always got to lower the microphone. Yes, so as Walt mentioned today, I'm going to be talking about LEMS-A3, which is part of the Artemis 3 deployed instruments, which is sending instruments back to the moon. So for those that may not know, LEMS is building on a history of seismometers on the moon. So every landed Apollo mission, it did carry seismometers, and Apollo 12 through 17 were able to build up a network. If you don't know why Apollo 13 doesn't have a seismometer, watch the Tom Hanks movie. But Apollo was able to give us really great details about what's going on the moon. So it was able to figure out that, yes, it is actually differentiated. So it does have a crust, mantle, and core, although it is debated whether or not the core is also differentiated. So is there an inner or outer core? Is there a partial melt layer? That we're not able to answer quite yet. It recorded thousands of moonquakes. So on Earth, we have earthquakes, moon, we have moonquakes. And these were came in a couple of different flavors. There were deep moonquakes, as the name suggests. They happen deep within the moon, and they're caused by tidal effects. There's more shallow events that are caused by the moon cooling and contracting. Their impacts, again, as the name suggests, it's from meteorites impacting the surface. And then there's also thermal events, which caused by the rapid heating and cooling of the lunar surface. So all of these events, a question I get asked a lot is, are they caused by plate tectonics like on Earth? No, the moon does not have plate tectonics, but it's still seismically active. And as you can see from this image here, the moonquakes themselves were not necessarily the best quality. These instruments are 50 years old now. The bit rates were much, much lower. So digitizing was not quite what it is to modern standards. Sampling rates were not great and not consistent. So there's a couple of issues with the data that Apollo was able to collect. Which is why there's a lot of new opportunities. So I've highlighted the ones that our team has been successful in getting. So there's Dolly and Matisse, and these are instrument development programs that will develop instruments from TRL-6, or excuse me, TRL-4 to TRL-6. Essentially, let's get these instruments flight ready. CLIPS Prism, which we have submitted to but haven't gotten selected for yet. They use commercial landers to bring sensors to the moon. And then Artemis, which we were successful in. It's a follow-on to Apollo. And what's special about Artemis is that it is going to be crewed. So we are going to have astronauts deploying our sensors on the lunar surface, which allows us to do things like be buried, which is really important for seismometers. But essentially, the University of Arizona at LPL for the seismometer program has raised over $12 million to bring these instruments from commercially available off the shelf instruments to being able to be selected for flight. So Artemis 3, as I mentioned, is going to be landing on the moon. So Artemis 2 should be launching next year. Artemis 3 will be the follow-on that will actually bring astronauts to the surface. It should be launching. I think our current one is July 2027. So it has been pushed back a little bit since we originally were proposing and then selected. It will go over this flight path and it will land at the south pole of the moon, which is quite different than Apollo. Apollo only landed on the near side of the moon and roughly equatorial. So being on the far side is allowing us to explore a whole new terrain that we have not seen before through seismometers. LEMS itself, which stands for the Lunar Environmental Monitoring Station, it is self-powered, it is autonomous. So once the astronauts go and deploy us, we will be providing our own power, our own communication systems. We have 2 seismometers that we'll be sending. One is a broadband BB, one is a short period SP. Essentially, these just sort of listen at different frequency bands, which allows us to record numerous different types of moonquakes that have different frequency content and signatures. So I have it pictured here, so you can see the astronaut can essentially carry us in what's about rough size of a briefcase, smaller than a carry-on bag that you would carry. And both instruments are encapsulated there. And we are solar panel powered. And right now we've been doing a lot of testing at the University of Arizona. So you've already seen a lot of photos of the ARB. Here's even more. About a week or 2 ago, we were doing some testing on our risk reduction units for shock and vibe. As of right now, we're doing a thermal balance test over in Kuiper using that red TVAC chamber. So this allows us to do a lot of instrument testing without having to necessarily send our instruments over to Goddard, which is the PI institution. So it's really handy that we're able to do all this right on campus. So there are a couple of science goals that we are going to try to meet. The first one is looking at seismicity. This is the where, when, and why are earthquakes happening. So pictured up here is a graph of where we think the different types of moonquakes would plot in terms of signal strength versus our detection capabilities. So everything that's above the red and blue lines are things that we can detect. And you can see that the blue and red lines, which are 2 different instruments, have slightly different sensitivities, which allows one to look at the low period versus the other one looking at high frequency, shorter periods. But depending on how long we're allowed to record for budgetary reasons, we can record hundreds to thousands of events. So the nominal mission lifetime is 3 months, but we do have the ability to survive for up to 2 years. So there's quite a range in how many events we can detect, but we should be able to achieve numerous seismic goals with those events that we do detect. So one of them is going to be looking at internal structure. So seismology works kind of similar to, if you think of sonar or X-rays, where as the seismic waves propagate through a body, we can look at these different phases and be able to essentially image the interior structure of the moon. So for example, in the left panel, you can see how different seismic phases might bounce off, say, a partial melt layer or the inner versus outer core. So whether or not we see these reflections can tell us if these layers are there, how thick they are, and what are the properties of them. So as the seismic waves pass through each layers, we can gain information about things like not just seismic velocities, but extrapolate that out to things like density, pressure, temperature. We can also look at hazards. So one of the big goals of the Moon to Mars program and Artemis is, can we establish long-term habitability or infrastructure on the moon? So as I mentioned, as the moon cools, it's going to contract and shrink. These can create these features that we see called lobate scarps or wrinkle ridges, and they could potentially pose quite the seismic hazard. So for example, if one of the nearby lobate scarps were to activate and create a shallow quake, plot on the right, you can see how strong that shaking is as a function of distance and how it is relative to lunar G. So you can see that, even within 20, 30 kilometers, you're getting pretty moderate shaking. If you're near, within 10 kilometers, you can have violent or severe shaking. Now, the question we want to answer is how often are these events actually happening and how strong are they happening when they do occur? So is this something that we need to be aware of and make sure that our structures can withstand these strong magnitude events? Or are they so rare that it may not be, something that we really need to take into account when we're thinking about how we build our structures and, ensure the safety of our astronauts? Oh, sorry, wrong way. So just to summarize, the University of Arizona, specifically LPL, will be supplying these seismometers, which will be on the next crewed mission to the moon. So we will be, for the first time in 50 years, sending seismometers back to the lunar surface. Our sensors are the result of essentially a decade's worth of development, which has been supported in part by the UASI. Our sensors are low mass, low power, and they are autonomous. They are also highly sensitive, making them an ideal planetary instrument for the lunar surface. We are also developing our instruments to do things like sense binary asteroids, and develop them for other bodies as well. So the data from LEMS, though, will be able to catalog our lunar seismicity, determine internal structure, and look at seismic hazard risks. So I do want to give a special thanks to our PI, Mehdi Benna, who was out at Goddard, as well as the LEMS team here at University of Arizona, and the A3 science teams. With that, I'm happy to answer any questions.
Thanks a lot. Are they need to be like anchored?
You mean like how will they actually be like deployed and grounded? Yeah, so our ConOps include the Artemis astronauts are going to be using a borehole tool in order to take cores of the lunar crust. So our SP sensor is small enough that it can fit in the borehole itself. So after they take a core to retrieve samples, they can then use an attachment to deploy our SP instrument into the ground. So it can, we're hoping for about 35 centimeters of burial. Our slightly larger BB instrument is going to be buried in a shallow trench. So that's also going to be on the order of about 20-30 centimeters beneath the lunar surface. And that will allow for good coupling, as well as also help regulate the thermal changes in the lunar surface for our instrument.
So do you plan to operate through the lunar night?
We do, yes.
How do you actually?
Solar power. Yeah. So our solar panels will charge batteries, and then the batteries are, yeah, are sufficient in order to keep us alive during the lunar night. So that's part of the reason we're doing the thermal balance test upstairs, is to see actually how much power we might need when we're, you know, really cold and things like that.
I was just wondering how much you think human activities would affect the measurements. If you put it far away, that's not an issue.
Well, the good thing is the astronauts won't be staying the entire time. So in seismology, there's a sort of phrase that we use: one person's noise is another person's signal. So what we can actually do is, depending on when we are deployed on the surface versus when the other instruments and other activities are ongoing, we can use the astronauts as a signal. So them walking around, we should be able to pick up. For safety reasons, we're probably going to not operate when it lifts off, so that we can, you know, protect ourselves a little bit from the blast. But yeah, we do anticipate that astronaut activities will serve as a source. That will only likely be for the first few days or hours, though. And then the vast majority of the rest of the mission will be operating without too much influence. That being said, if other things land near the South Pole, we could potentially use those as opportunities, much like InSight did on Mars. Great, thank you.